So, our first concern about can those multi-layers, because the temperature is quite near the dissolving temperature of multi-layer ammonia. So we made just a few trials, and so we can see we can form a multi-layer. Nothing else to say about it. We had to measure it on Mars 60 because on Mars 20 the signal is too high. But okay, but we are lucky we can form. So we made some TPD experiments. We tried with high energies like 900, 400, 150 at different times. So this is an example for 150 eV in 20 minutes. And we see we can form hydrazine, we hope so. We have the Mars 36, what is the deuterated hydrazine, and the 34 hydrazine minus D, and 32 hydrazine minus 2D. You have here the non-irradiated each for the 32, for the 34 and 36. And you see here the irradiated, where you get a signal at about 21,000 milliseconds. Microseconds, I'm sorry.
Can I just interrupt 1 second? So, what she's looking at is N2D4. Okay? So that, how do you think N2D4 is being formed? ND3 going to ND2 plus D. ND2 plus ND2 going to N2D4. Okay? This is hydrazine. This is an important component in rocket fuel. So we could blast off to the moon if we produce enough of it. So what she's saying is that N2D4, this is going to be 28 plus 4 times 2, 8. So this is the mass to charge ratio is 36. That's the parent molecule. Okay, so she's seeing the parent molecule 36. Then she's seeing the 34, which is N2D3 plus, and then N2D2 plus. Okay, so this molecule is fragmenting inside the mass spectrometer and forming those ions, and they're all lining up at the same time, at the same temperature. So this is one species coming off at this time, this temperature. This is so much nicer, cleaner than methanol.
Not to rub it in.
So other thing we were thinking about is if we get hydrozoic acid. We don't know how we get it anyway, but in photolysis or radiolysis photo experiments, it has been found, but we can't really say we find it because the problem is we have Mars 44, which is, for example, CO2 and many other products, and every other Mars, and you can monitor hydrozoic acid, is the signal so high that you don't see any peak at this. I want to try it again when we use the non-deuterated ammonia, so maybe we can see they can say that and say if we get it or not. But it's clearly another product than the 36 because we had another time. And it's from the same experiment. This slide and the slide before is completely the same experiment. It just
Let me just do a quick interjection here. So what she's looking at here now is N3D. Okay? We have no idea how this is formed. I told Megan she's got to figure this out by Sunday. Megan is not here. She's doing experiments on Sunday. So N3D, 3 times 14 is 42 plus 2 is 44. Okay? Every other fragment of this molecule has a contribution. So if we looked at, say, if we looked at 30, what would happen if we looked at 30?
Oh, we tested. The signal was so high that we can't see any.
The 30, why is the signal so high?
I don't know. I can show you the data. I have it here. I don't know. All right. I tried with 30. I tried with 18, with 16, with another month. I don't know.
Okay.
It was. Oh, the 30 is the problem. We have the 30 anytime monitored, but there is no peak in there. And we have a huge 30 signal, which is maybe formed in the mass spec, also in the ammonia blend.
Oh,
We had monitored 30 70 times, but 30 is also N2D2.
into, okay, all right.
It's
So,
a fragment of N2D2, 32, 30. So.
okay, so what Esther would like to do is to monitor N3H when we work with NH3, and then the mass to charge ratio would be 43, and 44 is a bad mass because carbon dioxide is 44, and there's a lot of carbon dioxide in the background in the chamber. So, you know, but I think I'm pretty convinced that she's seeing this and this. I shouldn't say she, all of you, seeing this and this. Okay, go ahead.
Okay, so as you told him, when we are finding something at high energies, we try to get it the same product at lower energies. So one energy we tried quite a lot was 90 dB because there's a resonance now which is leading to ND2 and to D. And so we tried several experiments with several times and tried to higher the current, but we haven't found it. With our designs, we haven't found it. It's nothing to see.
So this is 3 hours and 15 minutes. At 5 microamps, we've never done an experiment for this long with this high an current.
5 microamps for the plain crystal is just the maximum we got. This is thing.
Okay, I guess we have to wait. We've got to build something here to prevent this from happening.
Maybe I just go to this side.
Oh, you, okay, I see. Okay. Oh. Okay, just a couple of minutes, I think it'll arrive. Grab some food while I'm
Do you think that was the reason I sat there?
Huh?
You think I sat there because I was hungry?
Very funny, Esther.
Are you going home at all? Yeah. What is it? Yeah. We have that whole month. My family, sisters, I love them. Who are the others? No. My sisters are. Okay, sisters take lessons. That'd be good. Actually, I'll be like graduated, so I'll be actually. That will be a very intense time. Yeah. Especially my youngest one. That's how much you try. So the getting my best friend will be much but I think they say.
Almost there. Okay, thanks for coming, Natalie. Bye-bye. Is it back up there? Excellent. Oh, yeah.
Okay, I'm going to take away there. If you want to this side. try not to move? Okay. So we haven't found hydrogen at this energy, and we haven't found the hydrochloric acid. So we tried a slightly higher energy, like 50 dB, where we are above the ionization, but only slightly. And we evaluated, in this case, for 2 hours. It's an older experiment. The it was the first of the 3. And so we have made another experiment. This is 20 minutes, where we haven't seen any product. It's 2 hours. We have seen a small amount of the product. I'm not really sure with the time. So I haven't put the 32 here because you haven't seen it anymore. The signal was, I think the signal was just too small. So that means, okay, we can produce hydrogen at this energy, but only after really long evaluation times. And that was also with 2 microamps.
So 15 eV is above the ionization threshold for ammonia. 9 eV is below the threshold. So it just suggests that, electron impact ionization may be the mechanism by which hydrazine is formed. Go ahead.
We also tried an II experiment, but so it seems to be that we don't, the method is not sensitive enough to see something for our what we wanted. We had used 150 eV. First evaluate for 5 minutes, another 5, and so on to 20 minutes. This is the spectra of the non-evaluated ND3. That's quite, that fits quite good with what I found in literature. You have another metric stretch and some other IR resonances. We have seen the formation of a new peak. It's about 2,365, but it doesn't fit to hydrazine or diamond. So
NH2, how about NH2? It's an amide radical, NH2.
I have to have a look at it. I think not, but I'm not sure if I have the deuterated form of it. Might be.
Sorry?
Oh, no, if you were looking at NH versus ND, then that would, that's about 5 wave numbers different, I think, isn't it?
Oh, it's more.
It's more.
For the ammonia stuff, it's really a lot. We have this for the NH3 is over 3,000.
Oh, right.
Widely over 3,000.
Okay.
It depends. You have two masses, but the nitrogen is not so heavy itself. So if you okay, it's
I just couldn't remember how much of a difference it made.
might be different for a large molecule.
I just found in a paper the frequency for NH2, so maybe we can do a calculation.
But we need NH2 I have, I think.
Oh, you do have,
But I don't have ND2.
Okay,
Maybe.
okay.
I have to have a look and yeah. So, but I don't know, this is the only difference we have seen in the evaluation, so we have seen it a second time, so this seems to be, I want to try it again, but maybe with a higher energy.
IR is not as sensitive as TPD. TPD is probably at least a factor of 100 times more sensitive than IR. But the nice thing about IR is that you can collect the data at 100 Kelvin without heating up.
Okay. So now our last part was the ESD experiment, and so we tried to use we wanted to use the new electron gun. When you look here, that are how it should look. What I found in the literature, you have a resonance at about 5 to 6 eV and a broader resonance at above 9 eV. That's not exactly what we found. I don't know if the energy distribution, if this calculated right, that's another problem. But in this case, we found for the D minus and for the ND2 minus. Okay, this is also for the D minus and for the ND2 minus. So the resonances, yes, we found some strange energies, about 7 to 8. It's about here in between, and I think there were also differences if I have 4 or 5 masses. And we found several masses while we are doing it. I also monitored the 34 and the 42, just to have a look if we get maybe hydrazine or hydrochloric acid. And the strange thing about it was they lined completely up with this one sometimes, and sometimes we see even see some other event before, and I was a bit surprised because I don't expected this product, and I didn't expect, and if they came, I didn't expect them in that amount. So we made a test that we just said, okay, maybe it's a problem with the measurement, and we just take one mass which can't be, and this is mass 8. Because nothing has mass 8. And as you can see here, the signal for mass 8 is even larger than the signal for mass 18. So obviously we have a problem with the measurement, and it seems to be has to do with the electron, because after we have made a TPD experiment and also monitored mass 8, and we haven't seen any mass 8. So it seems to be a setting with has to do with the electron gun and the
not the electron gun. This has to be a problem with the mass spec, the setting for the negative ion lenses.
Yeah, okay.
Yeah, so it's a problem with the mass spec. We have to send the data to England and have them look at it. Something is not working correctly. We should not be observing anything at mass 8. Except, I mean, the only possibilities is, doubly charged time. Remember, when you're monitoring on the x-axis in a typical mass spectrum is mass to charge ratio. Sometimes you can form doubly ionized species.
That might be methane and or oxygen. Both of them is not really likely.
Yeah.
So
I mean, the first time we're doing these experiments, there's always going to be challenges, something new to keep us awake at night. So, questions for Esther?
So is it because of the position of the crystal, or?
we didn't know. We can't do these problems today. It's just, in the most of the days we were doing TPD and a little bit IR, and we just try to test with electron one. There are several problems till now. We're just figuring out a new method, something like that. So.
I don't think the position of the crystal can contribute to a signal at 8. I mean, this is something fundamentally wrong with the mass spec.
It wouldn't spit out really, okay?
Yeah.
You're right. So, it was just 2 hours ago, this experiment.
Yeah, right. Crystal, you had a question.
Well, when she said this experiment was just 2 hours ago, I was going to ask if it had the same problem with neutral or positive ions.
Yeah, we haven't.
Well,
I don't think.
this is just 2
We
hours
have worked
ago.
yesterday together. We have seen in the nucleus. We haven't seen any ions. You have seen it too. What's it? Oh no, okay, I'm sorry. This was with Katie. When we tried to get the nitrogen evidence, we haven't seen anything because the signal was so high.
Background 28 signal is
and
very
14
high.
is even more complicated because we have ammonia and isn't.
Yeah.
But so we can say about it.
But I think
I tested tomorrow with not tomorrow.
Yeah.
But maybe next time with positive ions.
Thank you very much, and there's more food. Please help yourselves, and thank you for coming on a Friday afternoon, late Friday afternoon, but I think everybody's on the same page now. Everybody knows what's going on, why we're doing what we're doing. Very good. Thanks again, Frida, for